This week in Mod 11, we are going to be looking at solving trig equations. At the top of your notes, I put the Pythagorean identities just as a reminder. You should already know those. And then I gave some tips on things that you can do to help you solve equations. If the equation is linear, that means that the function, the sine, the cosine, the tangent is to the first power. You want to just solve for the function. Get the equation to the point where you have sine equals this or tangent equals that. If the equation has multiple occurrences of the function, you have more than one term that has sine in it or that has cosine in it, then get all of the terms on the same side, set the equation equal to 0, and try factoring. If the equation contains reciprocals, set the equation equal to 0, and then multiply the entire equation by one of those functions to eliminate the reciprocal function. That means if it has both a sine and a cosecant, multiply the entire equation times cosecant and you will get rid of those reciprocals. If there are two different trig functions in your equation, but one of them is squared, see if you replace that squared version with a Pythagorean identity, and that will help make your equation easier. So the first example that I want to do is just the very basic equation of sine of x plus 2 equals 3. This is example 1 from your notes. Notice that our equation is linear, meaning the function right here, sine of x, is to the first power. In that case, we want to get the sine of x by itself. So we are going to subtract 2 from both sides and get the sine of x equals 1. So now what we want to ask ourselves is, what angle has sine equal 1? That's what you want to ask yourself. And there may be more than one answer. Well, the sine is 1 only at 90 degrees or pi over 2. If you look at the directions, it says to solve over the integral of 0 to 2 pi. That means that your answer needs to be written in radian form. So the angle that we are looking at is pi over 2. That's a very basic equation, but that's the idea of what you are doing in this section. Looking at example B, we have 2 times the cotangent of x plus 1 equals negative 1. Again, our function is to the first power, so this is a linear equation. We want to get the function by itself. So the first thing we're going to do is subtract 1 on both sides and get 2 times the cotangent of x equals negative 2. We still don't have the function by itself. It's still times a 2. So we're going to divide both sides by 2. So now we have the cotangent of x equals negative 1. So again, remember, we are asking ourselves, what angle has cotangent equal negative 1? That's what our answer is going to be. Well, cotangent is negative in quadrants 2 and 4. And the place where cotangent, where you put the x over the y and get 1, happens at the over 4s in those two quadrants. So the angle that we are looking for, x, is 3 pi over 4 from quadrant 2, and 7 pi over 4 from quadrant 4. On example C, we want to solve the equation that says tangent of squared of x minus 3 equals 0. We only have one term that has a trig function in it, so we are going to get that trig function by itself. So that means we're going to add 3 on both sides. So the tangent squared of x equals 3. Well, in order to get rid of the squared so that we just have tangent of x, we're going to take the square root of both sides. Don't forget to put plus or minus in front of your square root of 3. So when we simplify that, we now have the tangent of x equals plus or minus the square root of 3. So we want to find the angles where the tangent, putting y over x, will give us the square root of 3. Or if you want to think of it that way, you can remember that that equals the square root of 3 over 1. If we think about the fact that we want the plus and the negative, that means every quadrant will have a tangent value that is the square root of 3. Where does that happen? That happens at the over 3 angles in each quadrant. So once we decide that, we now say x equals what angles? Pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. On example E, we are being asked to solve the equation cotangent of x minus 1 times the quantity square root of 3 cotangent of x plus 1 equals 0. Let me go back to a basic algebra kind of problem that you would have done in the past. If you had something like x minus 7 times x plus 4 equals 0, that's already in factored form, and you would set each of the factors equal to 0. We are going to use exactly the same concept on this problem. This equation that we were given is already in factored form. So we are going to set each factor equal to 0. Now, looking at each of these factors, they are both linear because they are cotangent to the first. So we need to get the cotangent function by itself. The first one will just be cotangent of x equals 1. Where is cotangent positive? That's in quadrant 1 and quadrant 3. And we want the cotangent, putting x over y, to give us an answer of 1. Cotangent equals 1 at the over 4 angles in quadrant 1 and quadrant 3. So the angle x that we are looking for quadrant 1 is pi over 4, and for quadrant 3 is 5 pi over 4. On the second factor, we want to get the cotangent by itself. So the first thing we're going to do is subtract 1. We now have square root of 3 times cotangent of x equals negative 1. We still don't have the cotangent by itself. It's times the square root of 3, so we're going to divide by the square root of 3. So now we have the cotangent of x equals -1 over square root of 3. Cotangent is negative in quadrants 2 and 4. And so we're going to look in quadrant 2 and in quadrant 4. If we put the x coordinate over the y coordinate and simplify, where would we get -1 over square root of 3? That happens at the over 3 angles in those two quadrants. So x, our angle, is 2 pi over 3 and 5 pi over 3. The next problem we are going to look at is example H, where we are told that we have the square root of 1 plus cosine of x equaling the sine of x. Well, right off the bat, I know I need to get rid of that square root symbol. I can't solve for anything when I've got a square root symbol. So the first thing I'm going to do is square both sides. So I'm going to square the square root of 1 plus cosine x, and I'm going to square the sine of x. When you square a square root, you get 1 plus cosine x. When you square just the sine, you get sine squared x. Now we got rid of our square root, which is great, but when I look, I've got two different trig functions. I need this to be the same trig function. You can't solve when you have these pluses and minuses. You can't solve when you have two different trig functions. So I'm going to rewrite the sine squared by using my Pythagorean identity as 1 minus cosine squared. My left side is going to stay the same. My right side is going to become 1 minus cosine squared. Now that I have the same function, but I have a squared and a first, this is one of those cases where you want to get all the terms on the same side and make it equal to 0. In order to make this equal to 0, I'm going to subtract 1 on both sides, and I'm going to add cosine squared on both sides. 1 minus 1 is 0, so those have offset each other. Cosine of x and cosine squared of x are not like terms. This means we have to leave them as separate terms. So the left side will now become cosine squared x plus cosine x equals 0. What I need you to recognize here is that this is the same idea as if we had had x squared plus x equals 0. We can factor out an x from both terms and then have x plus 1 as our second factor. We are going to use exactly that same idea, but we are going to do it with a cosine of x. So we're going to factor out cosine of x. If I take cosine squared divided by cosine of x, I am left with just cosine of x. Plus cosine of x divided by cosine of x leaves us with 1 equals 0. Now I have two factors. Cosine of x is the first factor. Cosine x plus 1 is the second factor. So once you have factors, you set each factor equal to 0. So cosine of x equals 0. Cosine of x plus 1 equals 0. The first factor is already solved. It's just cosine of x equals 0. So we want to find any angles where cosine equals 0, where the x value equals 0. That happens in two places. The angles where that happens are pi over 2 and 3 pi over 2. On the other factor, it's not quite solved. We need to subtract 1 on both sides and get cosine of x equals -1. Now we want to ask ourselves, at what angle is the x value -1? That only happens at pi. So x equals pi. The next example that I want to look at is I, which is -1 minus the tangent of x equals the secant of x. When we have a problem like this one with two different functions in it, but neither one of them is a squared, you cannot substitute using a Pythagorean identity unless you have a squared. But when I look at my Pythagorean identities, tangent and secant do appear in the same Pythagorean identity. So in order to create that Pythagorean identity, I'm going to square both sides of this equation. So I'm going to square -1 minus tangent x, and I'm going to square the secant of x. Now remember that -1 minus tangent x, the whole quantity being squared, means I'm taking -1 minus tangent of x times itself. That means that I am going to need to use FOIL. So doing FOIL on this, if I take my first times my first, I'm going to get +1. If I take my outsides times each other, I will get positive tangent of x. If I take my insides times each other, I get another positive tangent x. And then if I take the last times the last, I get a positive tangent squared x. Going over to the other side of the equals, if we square secant, we get secant squared of x. I do have like terms, tangent of x plus tangent of x, on the left side. So in combining that, I will get 1 plus 2 tangent of x plus tangent squared of x equals secant squared of x. So now you have to decide how you're going to use the Pythagorean identity. What you have to notice is that on the left side, we already have a tangent to the first and the tangent squared. I don't want to substitute secant for tangent because I have a tangent to the first and I can't substitute there. So I'm going to go the other way and I'm going to substitute tangent squared, however that works, for the secant squared. So we're going to leave the left side alone. We have 1 plus 2 tangent of x plus tangent squared of x equals, replace the secant squared with what it's equal to from the Pythagorean identity, which is tangent squared x plus 1. Now, all of the functions that I have are exactly the same. So I am going to set this equal to 0 because I have squares. If I subtract 1 from both sides and subtract tangent squared from both sides, I wind up with 2 tangent of x equals 0. I still need the function to be completely by itself, so I need to divide by 2, and I get tangent of x equals 0. So now I have to ask myself, at what angle or angles will I get 0 if I put the y value over the x value? That happens at the angles of 0 and pi. The last problem of this type that I want to look at is J, and what's different about this one is instead of just saying x, we have the sign of 2x plus 1 equals 0. In order to solve this, you still want to get the function by itself. So we are going to subtract 1 and get the sign of 2x equals -1. If you go back to the problem that we just did for a second and think about what we had, we said that the tangent of x equals 0. And then we just said x equals the angle 0 and the angle pi. When we are solving these problems, we are always putting whatever comes right after the function, which is called the argument. We are always saying the argument equals the angle. Going back to where we were on J, we had that the sine of 2x equals -1. So we have to ask ourselves, at what angle does sine equal -1? That happens at 3 pi over 2. So now we are going to take the argument equals angle. So we're going to say 2x equals the angle 3 pi over 2. The problem is we don't want to know what 2x equals. We want to know what x equals. So now, in order to solve this for x, we're going to divide by 2 or multiply by 1/2. So if we multiply by 1/2 on both sides, we get x equals 3 pi over 4.